So our climate change lab. So our kind of objectives for today are to look at climate data. We're looking at temperature data. We're also going to be looking at CO2 data and what we're calling event climate data. So volcanic eruptions, El Nino, La Nina, southern oscillation events to see if they have impacts on climate. You're going to determine if and how the climate is changing. You're going to look for trends, and you're going to learn, I think, some new Excel skills. The data, I believe, is already downloaded in Excel to Brightspace, and you can take it from there. So it's important that when we talk about climate change, you know that we're talking about more than temperature. Even though today what we're going to be examining is temperature, temperature is something that's easy for us to track, so we usually use it for looking at climate, but climate also deals with rainfall amounts and with air mass movements and humidity and wind and other factors. So when we talk about a shift in climate, it's not just that something is getting warmer or something else happening there. And it is safe to say that the temperature of the Earth's oceans and the atmosphere is changing. Some of it is related to air pollution. Some of it's related to deforestation. And then there have been some natural changes too. So what types of natural factors affect climate change? What types of natural factors do you think affect global temperature? What might happen naturally that would change the temperature? Anyone think volcanoes? We got some maybes and some no, definitely not. How about El Nino? Does that change global temperature? At least in the short term? Anything else? Does the sun change global temperature? Yeah. So our average temperature and climate in an area is going to change over time. And by time here, we mean long-term time, like geologic time, hundreds of thousands, millions of years, things like that. Because we do cycle between ice ages and interglacial warm periods. What are we in right now? An interglacial warm period. We're between glacial times. There have been scientists that have suggested we should be entering into the next ice age, but we're not. Whether or not they are wrong in their prediction or whether or not it's just simply too warm for that to happen, we're not sure. The Earth has what's called an elliptical orbit around the sun. With an elliptical orbit, unlike a circular orbit, it means that sometimes the Earth is closer to the sun than it is at other points in time. This orbit, however, changes. There is some variability in it, and right now, the Earth's orbit isn't actually the big concern. The variations in the orbit happen about once every 100,000 years. Right now, the sun's activity, and if you want to know about this, talk with Dr. Bradstreet. The sun is acting strangely. It is not reacting normally in the way they expect things to be occurring. And he thinks that that is likely related on some level to what we're seeing with temperatures. And he's probably right. If anyone knows if the stars are acting irregularly around here, it would be Dr. Bradstreet. And when he tells me that it's acting strangely, I believe him. And there are astronomers that are worried about why the sun is acting strangely. Because that means that sometimes it's going to be throwing off more heat, and does that mean that other times it's going to be throwing off less radiation? And what will that mean for us? But the Earth is also tilted towards the sun. Our normal angle is 23.5 degrees. But if our tilt decreases, we warm. If our tilt increases, we cool. So just that change in the tilt of the Earth's axis is going to determine whether or not we warm or cool. And then the solar activity is mentioned up there. The sun's solar cycle is about 11 years, but it's been behaving strangely for slightly longer than that right now. The increase and decrease in volcanic activity. We're going to check this one, but it's important for you to know the volcanic activity does produce immediately heat. It does, but it also produces a lot of ash. The ash goes up into the atmosphere, and the ash could react in one of two ways. It could trap heat in, if the heat is on the inside of it, but it also has the ability to trap heat from coming in because it forms a large cloud that can actually help reflect the heat back out and would thus lead to cooling. And then we have one of the phrases that I'm not even sure what to do with sometimes, chaotic interactions of the climate system. What does that sound like to you?
Crazy weather.
Crazy weather. Things are interacting with each other in ways that we don't understand. There are things called the Milankovitch cycles that deal with the orbit of the Earth around the sun, and there's 3 different sets of cycles that can be in phase with each other or out of phase with each other, and that can react to some of these or that can cause some of these chaotic cycles. One of them is like a 27,000 year phase, another's 43,000, and I think the third is 110,000. And they can be together or they can be opposing, which will change what's happening in the climate. But then there's things that are bigger than that. There's the proportion of water in the ocean versus in the atmosphere. There's the amount of land space that's exposed versus the amount that's covered, which is going to relate a little bit to solar gains. Then there's complex, unpredictable interactions. How right do you have to be to make a weather forecast? Well, let me start this question a different way. How right do you have to be in biology to say that things are related to each other? What percentage right do you need to be? Or percentage certain? Take a guess. Tell me what number you think we need to be.
90.
Above 90. 95 is the lowest, but keep going. 99.5%. When we look at a p-value of 0.05, we're saying that we're 99.5% certain that something is right. So we're usually 99.5% certain that something is not by chance. How right do you have to be for weather forecasting? Higher than a 10% chance. Give them more credit.
80.
Lower than 80.
65.
Lower than 65.
40.
Lower than 40. One of my geography professors in undergrad told us that for the meteorologist that he knows, you can have a minimum of a 30% certainty to make a forecast. And let's say it's even 60%. Who's been listening to the weather forecast for this week other than me? Because let me tell you, I want to have my 152 lab on Wednesday because we are dissecting hearts, darn it. And it's cool.
That's a good time.
And Gabby, what you don't know is we use fresh organs for dissection. They're not preserved. They're not human hearts, clearly.
No, that's what I thought.
Clearly. But it's really fun, and it's really interactive, and they don't freeze well.
What are the pigs?
Pig hearts. Dr. Lutz picks them up from a butcher in Lancaster County for us. And it's really amazing. That's how we also get lungs and kidneys and eyeballs. They're very cheap, but they don't smell of chemicals. So it's a huge win, and they look real. But every time I check the weather right now, there's a new forecast for Tuesday into Wednesday. The forecast I just checked in my office said 1 to 3 inches of snow on Tuesday, followed by another 3 to 6 inches of snow on Wednesday. which makes me sad. The forecast last night was we might get a little rain, no snow. I'm very confused.
I got a notification like as I was walking in, and it was like, oh, 8+ inches of snow expected on Wednesday. And I was like, all right.
No! But this is part of the problem. People sometimes don't believe that climate change is real because weather's not predictable. And they confuse the words climate with weather. Weather is what is the temperature today? What is the precipitation like today? It's short term. When we talk about weather trends, we're usually talking about less than 10 years. When we talk about climate, we're talking about things that are centuries usually of information. So climate is long term. Weather is what do I wear flip-flops or snow boots today? And I really want to be able to leave my coat in the or leave my coat at home when I come to school in the morning. That's what I really want. At least leave the winter coat. Be nice, but we're not there yet. Which is also strange, I feel like. Although today's the first day of spring, or tomorrow is the first day of spring, and snow. The ocean and the atmosphere also interact in very strange and sometimes unpredictable ways because they feed off of each other with the exchange of water, vapor, and temperature. And these chaotic systems can result in cooling or warming, and some of them are long-lasting in the idea of decades to centuries. So I'm going to be using some images from an old Pearson book I used to use that ethically I had a lot of problems with, but their graphs are fabulous. So if you see strange pictures, sometimes in other lectures I've taken it from them, but they said some ethically horrific things about how to handle population control, and I decided I couldn't teach from it. They were perfectly okay with us just doing away with a whole bunch of people is not a bad thing. It's bad. Their science was good. Their ethics were a disaster. So this is showing you two things here. Atmospheric CO2 on the top, surface temperature on the bottom from 1950 to about 2007. What do you see? So they look like they agree. They're both going up. Is there full agreement? No, there's variability. This is just a snapshot though, right? We need to see more data. This is not enough to make any single decision from. This is just showing us the 2001 to 2007 mean surface temperature anomaly, which is the difference from what is expected. The global mean was 0.5 degrees Celsius warmer than normal. We're around there in the 0.4 to 0.8 range. Is anywhere colder? Surprisingly, part of the Atlantic coast of the US is a little colder. A few other places of cold. I'm not convinced that the black block in the middle of Saudi Arabia is real. That may be an area of no data, or it could be real. Is most of the world warmer? Let's look and see what that looks like. So this is looking at 1900 through 2000 data. The black line is your temperature anomaly. The, I believe, dark green is what would be expected with natural factors only, and the light green is with human and natural. Some places have gotten a lot warmer than they should have been. At some point in time, you have to, I think you all already have grappled with this question, but other people are going to be thinking about it and asking you because you're a scientist for your thoughts. Equally as much for those of you that are environmental science majors that they will later in life ask you your medical opinions on things because you took some biology classes. You've taken science classes, you are a scientist, you must have an opinion. and your opinion is educated because you are a scientist. So the question is climate change occurring? Well, glaciers are melting at record rates. The Antarctic ice sheet is breaking up on a regular basis, and last year we had a glacier break off that was the size of the state of Delaware. Delaware's tiny, but a glacier the size of Delaware is not. The Arctic polar ice has had a 10% reduction per decade since the, I think, 1950s-ish. It's 40% thinner now than it was in the 1970s. So it's shrinking in size and it's shrinking in thickness. There's heat waves and extensive droughts all over the world. Having said that, surprisingly, the precipitation worldwide has increased 1%, which means some areas are in drought and others are in flood. The largest decline of rainfall has been in the tropics, which is strange because that's where we should see the most rainfall. There's been a rise in the number of tornadoes and violent storms. There's been changes in precipitation. And gosh, I need to look up this data better. This is really old data. At one point in time, it was 10 of the hottest years on record have been between 1990 and 2003, but I believe it's now that the 10 hottest years on record have all been since the year 2000. The question becomes, is this a coincidence? Or is something happening? Okay. There's a strong correlation between the increase in atmospheric CO2 and other greenhouse gases and the Earth's surface temperature. But we see the strongest correlation between CO2 and temperature. Do you know what the IPCC is? International Panel on Climate Change. It was convened by the UN. It is it might be intergovernmental, not international. It is an intergovernmental unit. It contains scientists from multiple countries, many countries all over the world, and it included atmospheric scientists, it included chemists, it included oceanographers, other type of people whose job it is to crunch this data. It included data from a variety of sources. It included the review of lots and lots of other scientist studies. And they were intensely focused on figuring out what is happening. Because there are natural reasons for climate change, but human sources, they found, were influencing climate change more than were natural sources. We've had computer models that we built computer models that we sent kind of back. We set them back to the year 1900, and we asked them to forecast what climate would have been based on conservative, natural-only effects. And we found that natural climate change could not result in the temperatures that we have today, that the natural things were not enough to get us where we are. Additionally, we found that the human-only factors were also not going to give us the same climate that we see today, that there's an interplay between natural factors and human factors, with one moderating the other. But natural factors were not the only way that we could get to the temperatures we have today. What types of projected impacts are we going to see from climate change? The Earth is going to warm, and the climate's going to shift. Things are going to become hotter and drier, except for some places that are going to become cooler and wetter. And that's that whole climate as opposed to global warming. Further temperature increases are going to make dramatic shifts in climate, and that's actually some of the big concern, is that species won't be able to move fast enough to keep up. The IPCC predicted that by 2100, we would see between a 2 and 4 degrees Celsius increase in global temperatures. It may now be 5 degrees or 6 degrees, they've also talked about as well. Having said that, there's a range because we don't know how quickly things are going to happen or whether they can be mitigated by made less by human activity. And we expect that there will be between 8 and 24 inches of sea level rise by the year 2100. Reducing carbon dioxide is not enough. There's other pollutants that are involved. Methane is a big concern. The nitrogen gases are another big concern. And then there's the fact that carbon dioxide actually lasts less time in the atmosphere than does methane and these other gases. So reducing them is going to be important to actually see a long-term reduction. But there's some beneficial effects of climate change. The cost of heating your home will decrease. It's true. It will. What do you think about that? Is that a cost of your home decreases? Is that a good benefit? Sure. It also means that we will be burning fewer fossil fuels in the winter. Okay. Fossil fuel demand is going to decrease. The tundra may become suitable for human settlement. Natural ranges of things will shift poleward. Why does that matter? Because more tropical things are going to come up here, and it's great. It is. It also means that there's going to be higher biodiversity in the mid-latitudes now, and that is a good thing. There are going to be some areas that have a massive increase in rainfall. There's going to be a much longer agricultural growing season for the mid-latitudes and the upper latitudes. We may be able to grow crops for 2 to 4 months longer each year. So we may be able to do agriculture almost year-round. That is a massive benefit that will allow us to feed more people. And photosynthesis is going to increase 0.5% for every 1% increase in CO2 concentration, until we get up to 100 degrees Celsius, and then it's going to rapidly decrease. And if there's an increase in photosynthesis, then it will sequester more carbon dioxide, and it will start a negative feedback system, and that will be good. Are these benefits? How do you feel like I'm selling you like the used car on the lot that like doesn't have any tires? But I'm like, it's okay because you can sleep in it. But some of these are really good effects. And here's another thing. How many of you like summer? How many of you dislike winter? Or dislike snow? There will be less snow. Isn't that good? Effects. The summer cooling demand will increase and you will burn more fossil fuels. Flip side. We're going to have an increase in the melting of ice caps and glaciers. Sea levels will rise, and the sea will move inland. Someday, Philadelphia, Eastern for that matter, could be beachfront property. That's right. Goodbye, New Jersey.
That's all good things.
Is anyone from New Jersey? Is anyone going to be sad if we lose New Jersey? Good news. We're going to lose Florida and Louisiana way before New Jersey. Hannah is like crying on the inside about Disney right now. As sea level rises and the water moves inland, it's also going to move up estuaries and it's going to move in the groundwater, salinizing aquifers. Many of the areas worldwide where we grow rice are going to become salinized, making rice production problematic. And considering just how much of the world relies on rice as their main grain, that is going to cause food riots and massive instability. There's going to be an increase in the amount of hurricanes and tropical storms. There will be more of them. They will be stronger. They will be less predictable. They will cause more damage. Some areas become warm and dry. Others become cool and wet. And it's going to greatly alter how we do agriculture. We expect that the Midwest of the United States will become a dust bowl once again. Estuaries will have an increase in salinity, which will decrease their effectiveness as nursery grounds for growing animals. There will be massive extinctions of organisms that cannot adapt to climate changes, with coral reefs we believe being one of the first victims. Tropical diseases will spread as organisms move further poleward. Floods and droughts will impact human health, and there will be massive economical and political impacts and instability due to these effects, almost entirely due to changes in agriculture and water. Apparently oh good. My slides look right now different than yours. It stopped moving on my computer and I was like, a whole nother slide of harmfulness? That's enough. But here's the problem. We don't know how quickly any of those things are going to happen. We know some of them are happening today, but we don't know how bad it's going to get. And now it's important that we take a look at the data and the predictions. So this is looking at data from 400,000 years ago through until, well, about 1950-ish. That zero is 1950. This is data from NASA. I'm going to comment that the last time I checked all of these links, they worked. I haven't checked these links since January. Just putting that out there. Because some of the websites no longer have climate data on them. I'm going to leave that statement there. It's safer for me to leave that statement there. If you want to talk about that, we can talk about that later. But for right now, I'm going to leave that statement there. No, I'm also going to mention one other thing. I'm not faulting either political party for that. I'm not. Because the removal has not been an act of Congress. And that's where I'll end. CO2 has never been above that line in human history. And that's a pretty fast change. Has CO2 ever been above this level? Yes. Has CO2 ever been above this level when humans were alive? No. And that to me is where there's a big difference. This is looking at temperature in blue, CO2 in green, and dust particles in red. It's a little strange, but trace the lines. Take a moment. Do any of them agree? Or mostly agree? Does dust agree? Is it possible, though, that dust is impacting it? Because look right here. There's this very high bit of dust, and then there's an increase in temperature. There does seem to be some interplay between this data. Because remember I said that natural alone could not account for climate change? Neither can human alone. That there is some interplay in here. That when we've looked at the data, it seems that these chaotic interactions are real. But dust doesn't really track well because there's a couple times when dust is really low and temperature is really high, and then dust is really high and temperature is really low. So it's strange. Is there some level of agreement, though, between CO2 and temperature? Some. This is looking at surface temperatures over the last 1,100 years, and it's using multiple different proxies here because it's not enough that we measure temperature in one way, and because in part the scientists working on climate change data want to be sure that we're measuring it well. Borehole temperatures are one way that we've measured temperature. So we're going back in time and looking at, oh gosh, that study, I forgot exactly where it's done. We've used trees, we've used ice. You can actually take a column of ice, and the glacial lengths are used with this too. But you can take a column of ice, you can drill down, and you can tap into it and pull out the air pockets. There's little air bubbles in ice everywhere, and you can sample directly from when that ice was made what the gases in the air were like by tapping into that bubble. So we utilize the glacial air bubbles, and we then correlate the ice forming with rates, and we can figure out times. It's kind of crazy. We use multiple proxies a lot of times because one is just not enough. So we use information from ice, we use information from tree rings, we use information from human records. So we use a lot of different lines of evidence for tracking This is looking at temperature change in the northern latitudes, low latitudes, southern latitudes, and the US. Each of these graphs is on a different scale. Where have we seen the highest change in temperature? Which we fall into, but we haven't seen the same effect. And these are mean temperature anomalies. We don't take them for just one place and take them over a time period. We average them for a year, and we look at the data that way, because you can have, as you're well aware, a hot day and a cold day and things like that. But we can expect, and have you ever traveled abroad or even someplace in the US and like looked at what is the average weather like there to pack your suitcase? Have you ever been really wrong? My brother-in-law just went to Ireland, where the one place he was got 17 inches of snow in one day. They didn't know what to do. He said the people didn't have any salt or shovels. They were using garden spades to like push the snow away and table salt to melt the ice, because they'd never had a snowstorm like that since like before 1950. They just had this same time that we had the wacky snowstorms. And at one point he wasn't going to be able to fly home from his business trip because they had the airports and everything closed down because they had not enough snowplows. He did not pack appropriate clothing for his trip entirely, because when he looked, it was like, oh, it'll be in like in the 40s and the 50s. And instead it was like freezing and snowing every day. But we can use that data, and we use that data all the time. Do you watch the news and weather reports when they tell you, okay, well, these are the average highs and lows? We keep track of this. This is looking at the link between global temperature and carbon dioxide concentrations. This is also called the hockey stick graph. If you read about it in things, this is what the hockey stick graph is. You can see that there is a correlation. I can almost guarantee that this is no longer posted on that website. This is looking at the temperature changes in the lower 48 states. So this does not include Hawaii. This does not include Alaska. From 1901 to 2009. Red is warm. Have most of the red years happened within your lifetime? Have most of the red years happened since 1980? So something is probably going on. Or we're in a very strange time period. Those are your two options. No, there's a third. The science is wrong and the data is a lie. So what are we seeing? The Greenland ice sheet is melting faster than it has in the past. The rate of temperature change isn't great. The ocean's acidity is changing too, because this is related to climate change and CO2 levels. Things are becoming more and more acidic. More acidic, lower pH. And most places we're seeing between a 0.07, about a 0.07 decrease in pH. So not much difference, but some. This is looking at Arctic sea ice and the Muir Glacier. These pictures were taken, my understanding is, in the same season from the same locations. I want to see if I have what season in my notes. Of course not. If you want to know the season, I can look it up for you. I have it somewhere. This is looking at snowpack in the Pacific Northwest, which has decreased steadily since the 1950s in most places. It has increased steadily in a couple other places. That's the fact that things are changing in different speeds and different ways. The length of the growing season has increased since the 1900s. That's good. We can grow more food. That's important. This is looking at sea level rise. The red is if we see a sea level rise of less than 1.5 meters, the places in red will still be underwater at 1.5 meters of sea level rise. The places in blue will go underwater between 1.5 to 3.5 meters. And the white did not come up well, but if things are white, it will be underwater at 3.5 meters and above. Do we expect to see this? No. But we're seeing right now changes of millimeters to centimeters, depending upon where you are in the world of sea level rise each year. This is what we expect our change in precipitation by the end of the 21st century looks like. And this is in inches of liquid water. They say liquid water so that it's standardized to rain as opposed to snow. So now you're going to look at data. You can see if you see the same thing or different things. The question is, will you learn to love Excel? And you're going to see what climate may